gas flow rate is 100. Mole fraction is given to us. The liquid flow rate entering is 300. Calculate the amounts and compositions of the two outlet streams, assuming that water does not vaporize into the gas phase. Okay, so let's make sure we understand the question. You've got a single stage process. Okay, it's a single stage process. You are given the information in terms of pressure. Okay, we know what the streams coming in are. The first stream, you've got air and CO2. The second stream that is coming in, you've got water. Okay, you're given the inlet gas flow rate 100. What does that mean? Inlet gas flow rate. It is the flow rate of the combined gas. In other words, it contains the CO2 and the air. Okay, so it is a combined flow rate coming in, CO2 and the air. You're also given the mole fraction of CO2 coming in with the feed. What are you asked to determine here? You are asked to determine the amounts and compositions of the exit stream. Okay, the amounts and compositions of the exit stream. So that's what's required from the question. Anyone confused about what the question entails, what the question wants? Do you understand? You comprehend exactly what the question needs? Okay, I assume you know what it means. Okay, so let's now put it into a diagram. Here's your single stage. Okay, coming in, you've got L0. Coming in on the top there, you've got V2. Here you've got L1, there you've got V1. And what are you asked to evaluate is the L1 and the V1 flow rates together with its composition. What's very important here as well is that the flow rates are given to us in moles per hour. So it is a molar flow rate. And remember, we said that when we're working with the absorption and later on with distillation, we always use a mole basis. Okay, always use the mole basis. So therefore, in this particular example, we don't need to convert. We don't need any conversion because it is already in the molar basis. So let's now put down the information that we've got. And what information do we have? You are told that the gas flow rate, and remember gas flow rate is the combined flow rate, is given to us as 100 kilogram moles per hour. So V2 is equal to 100 kilomoles per hour. What else are you told? Liquid flow rate coming in is 300 kilogram mole water per hour. 300 kilomoles per hour. Okay. What other information are you given? You are told that the mole fraction of CO2 coming in is 0.2, 20%. So YA2 is equal to 0.2. You with me, people? Anyone confused? Okay, so that's what's given to us. Now we're going to make a few assumptions. Now remember, when we doing writing this in a test or in an exam, you don't need to necessarily write all the assumptions, and the reason is because it's sort of understood that these are the assumptions that you are making. So therefore, we don't spend time writing all the assumptions, etc. However, in your assignment that you will get, you must list down everything, all the assumptions. You must justify the assumptions. It must make sense. Okay, in fact, there's an indicator there to check whether you are taking into account all the assumptions and you're making reasonable assumptions. So therefore, as a test or assessment to establish whether you are meeting this soft skill, this graduate attribute of problem solving, shows that you go through it step by step and you take everything into account. Okay, so that's very important. You are not told anything about whether the water that's coming in has any CO2. Although you're told that the flow rate is 300 kilomoles water per hour. Okay. So our assumption is that the water that's coming in is pure water and it doesn't contain any CO2, or if it does contain any CO2, it is negligible. Okay, that's a very important assumption. And if you are not given any information in the question that alludes to the water coming in having any of the solute, then that's a natural assumption that you make, okay, that it doesn't have any CO2. So if it doesn't, then we can assume that XA naught here is 0. If XA naught is 0, then this L naught equal to 300 is actually equal to L prime. What is L prime? L prime is the flow rate of the inert liquid. Okay, so in other words, that L prime will not change. So if I've got L prime equal to 300 on the left hand side, on the right hand side coming out, L prime will also be equal to 300. Right. Let's do the material balance. For us to write the material balance, what is the equation? The equation is L prime into XA naught over 1 minus XA naught plus V prime into YA2 1 minus YA2 L prime XA1 1 minus XA1 plus V prime YA1 over 1 minus YA1. That's my equation. Okay, so now I've got to establish and put down what is known and what is unknown here in this equation. So what do we know from this equation? We know that L prime is equal to 300. So L prime here is 300. What is XA naught? XA naught is the flow, is the composition of the water that's coming in. So it is 0. Okay. Plus V prime. We don't have V prime. How do we find V prime? What we do know is V2. V2 and V1 will be different, but V prime will be the same on both sides. V prime is the flow rate of the inert gas. Inert gas in this case is A, so it is the flow rate of A. Okay. If it is the flow rate of A, what's given to us in the question is the total flow rate, the flow rate of A and CO2. So I want to find out what is the flow rate of A only. Then V prime, I gave some equations last week. V prime is equal to V into 1 minus Y. Okay, so what does that mean? V is 100. 1 minus Y is 1 minus 0.2. That gives me 80 kilomoles per hour. So what is this telling us? Coming in is 100 kilomoles per hour. That is made up of 20 kilomoles CO2 and 80 kilomoles per hour of A. That's what it means. Okay, so the V prime, the inert, is 80. Remember, the 80 will be what's coming in and what's going out. It'll be 80. Okay, so let's put that into the equation. That's 80. into Ya2. What is Ya2? 0.2. 1 minus 0.2. And then on the right hand side, you've got 300. Now we don't know what XA1 is. This is what we need to determine. XA1, 1 minus XA1 plus 80. And we don't know what Ya1 is. So you've got this one equation only, and there's two unknowns. There's XA1 and Ya1 that are unknowns. So now we need another equation. Where do we get that other equation
from Henry's law, sir.
Say again, from the
Henry's law.
Henry's law. Okay, so the equilibrium equation. This is the operating line. Now you want the equilibrium equation, which is Henry's law, and that will help us to give us another equation that relates X to Y. Okay, so what is Henry's law? Henry's law says, let me write it on this side. Henry's law is PA equal to HXA. Okay, but we don't want it in terms of PA, because in my equation on the side, we've got XA and YA. So I want the equation in terms of XA and YA. How do we convert it? It means that YA is equal to H prime XA. And what is H prime? H prime is basically the Henry's constant divided by the total pressure. What's your units? Okay, you must be consistent with units. Okay, so what is Henry's constant? We know from the tables that at 293 Kelvin, given the temperature, 293 Kelvin, H is equal to 0.142 times 10 to the 4. Its units, atmospheres per mole fraction. Atmospheres per mole fraction, but I want to convert it to H prime. H prime will be mole fraction gas per mole fraction liquid. So I've got to divide this value by the total pressure. What is the total pressure? 1. So I'm just dividing the entire thing by 1 atmosphere. Okay, and you can see that Henry's constant works out to be, let's write it on this side. Ya1 is equal to 0.142 times 10 to the 4 XA1. Okay, now you've got two equations, two unknowns. You'll be able to solve them simultaneously. I'm not going to do that mathematics. You can do that on your own. And you'll get answers of XA1 1.41 is 10 to the minus 4, and Ya1 equal to 0.2. So we solved one part of the question, because the question was calculate the amounts and compositions of the two outlet streams. You calculated the composition. Now you just need to calculate the amounts. What are the amounts or the symbols? It is V1 and L1. What are the equations for this V1 and L1? Simple. You know what L prime is and what V prime is. So you just want to work out what L1 and V1 are. Okay, so let's do that. L1 will be equal to L prime over 1 minus XA1. You got L prime, you got XA1, you just calculated it. Put that into the equation and you get 300 kilomoles per hour. V1 equal to V prime over 1 minus Ya1 equal to 100 kilomoles. Okay, so you solved the problem. You solved it. You calculated the flow rates, L1 and V1, and you calculated their compositions. Now, if we look at the question, we see that coming in, you had 300 kilomoles per hour. Coming out, you also got 300 kilomoles per hour. On the top, 100 kilomoles per hour. Coming out, you also got 100 kilomoles per hour. What does that tell us? It tells us that the concentration of CO2 is very, very small.
Sir?
Yes. Yes, question. Hello? Okay, someone, I assumed had a question. Can you still hear me? Hello?
Sir,
Yes.
people are unable
Yes,
to access the
how
class. What to be done?
People are unable, sorry, you're breaking up. Say again, people are unable
They are
to?
unable to access the class.
People are unable to access the class.
Yes, what must be done?
Because of the link, or what's the problem?
We can't find the class. I myself struggle to find the class.
Okay, I sent the link very late. So do me a favor. Okay, let me put it onto the WhatsApp group. What you'll have to do is, I see people saying things here. Go to the Teams class. If you go to the Teams class on MS Teams and click on calendar. You should be able to find.
Sir?
Yes.
How did you got YA1, which is 0.2?
Okay, we'll do that now. Okay, I'm hoping what I typed on the WhatsApp, people will be able to join the class. Yeah, as I said, I sent that link actually just before 8, so it was quite late. When the link is also sent out to you, it will come to your email, and from your email you'll be able to click on the link and join the class. That's a normal procedure. But if not, then on the day of the lecture, if you go to your calendar, you'll be able to find the link on the calendar. I don't see people joining in. Okay, Ms. Ntungwa, are your colleagues able to join? Okay, I don't see people joining in after I type the message. But we've got, at the moment in this class, we've got 32 people. Okay, now I can see more joining in. Okay, great. Let's get back to our problem. So how did I calculate YA1? So in this problem, you've got two equations with two unknowns. Let's change the color here. You've got this one equation here, and the only unknowns there is XA1 and YA1. So there's two unknowns there. In my equilibrium equation, there's two unknowns. There's the equation here. There's two unknowns, same two unknowns, YA1, XA1. So this is simultaneous equations. Okay, I'm sure you've done this in maths, simultaneous equations. And that is how we calculate XA1 and YA1. Does that answer your question? Whoever asked. All right. So we're trying to analyze the question now, right? We're trying to analyze the solution, the answers that we've got. And what we found was that L1 was 300, which was the same as L0. V1 was 100, which was the same as V2. And what it is telling us is that the CO2 concentration is very, very small. So there is absorption taking place. You are removing CO2 from the V2, okay? But the concentrations are very, very small. And it shows that, right? 1.41 times 10 to the minus 4. Okay, it is very, very small. So because of that, it's a single stage only. The liquid and the gaseous streams are very dilute. Okay, and that is why you're getting these values. If I want a greater absorption to take place, I need to use more stages, multiple stages, in order to remove more of the CO2 from the gas. People, any questions with this one?
Sorry, sir?
Yes.
Can you just go over why we use the L prime equation again?
Okay, so there's two ways of doing this problem. I can use the normal traditional equation, just the mass balance equations, right? L0 plus V2 is equal to L1 plus V1. And then do a component mass balance there and get the same answers basically. The reason we use this equation, especially for absorption, is because it becomes easier when you've got multiple stages. So in multiple stages, we know that the L prime, which is the inert value, is consistent throughout the entire tower. Similarly, V prime is the same throughout the tower. It doesn't change. It is the inert gas throughout the entire column, so it doesn't change. And therefore, it becomes easier to use this equation when you've got multiple stages. We can't use this equation next section when we talk about distillation, because in distillation, the total flow rate, there is no inert. All the components exist in both the phases, in the gas phase and we call it the vapor phase. So in the vapor phase and the liquid phase, the components exist in both the phases. Whereas in absorption, you've got inert values. So it doesn't mix. The air doesn't mix with the water. And that is why we use this equation. Any other questions? Okay, let's carry on. Let's look at countercurrent multiple contacts. Okay, we had these equations before in the first section on equilibrium studies, but we'll just go through it briefly here again. Component A is being exchanged between the V and the L streams. The V stream is composed mainly of component B and the L stream mainly of component C. So we assume that the C and the B do not mix. Only A, which is the solute, moves from the gas stream to the liquid stream. Components B and C may, well, it says may or may not be somewhat miscible in each other. In our calculations, we assume that they are non-miscible. They do not mix. If you have to do a total material balance, L0 plus Vn plus 1. equal to Ln plus V1. Okay, and that's equal to M, which is my total throughput. Do your component mass balance, you're just working out the composition of component A coming in. Okay, A coming in. If we make yn plus 1 the subject of the formula, now you're doing a balance from the first stage to the nth stage, somewhere in between. And remember, n can represent any stage from 1 right up to capital N, which is the total number of stages. If you do that, that is the equation you get for the component mass balance and for the total mass balance. You make yn the subject of the formula, yn plus 1, sorry, the subject of the formula, and that is the equation you get. And this is the operating line. Remember what we said about the operating line? The operating line relates compositions on the same side of a stage. Okay, it represents compositions on the same side of a stage. Let me change my color here again. So I've got yn plus 1. Where is yn plus 1? It's there. And where is xn? Xn is here. So you can see it is on the same side of the nth stage. Okay, so this operating line relates those two, relates the compositions as they pass each other. They're passing each other on the same side of a stage. Okay, as you can see here, they're passing each other. The equilibrium line, what does that do? It relates compositions that is leaving the equilibrium stage. So it will relate xn to yn, same subscript. It also relates all the other ones. So you got L2. Sorry, let's use composition. So it'll be x2 and y2, x1, y1, and so on. Okay, it goes across the board. Operating line and equilibrium line. If we plot this yn plus 1 versus xn throughout the entire column, that will give me the operating line. If I plot yn versus xn, that will give me the equilibrium line. So you'll have two lines. One is the operating line, one is the equilibrium line. If we put it into the tower, there's the tower here. You've got the liquid coming down. We always represent liquid coming down and gas going up. Why is that the case? Why can't we change it around and have vapor coming down or gas coming down and liquid going up?
Because the gas is lighter than the liquid, so therefore it goes up.
Exactly. Okay, so it's because of the density difference. The gas is always lighter than the liquid, so therefore if I try to put in gas here on the top, it won't go down the column. Okay. Similarly, if I put in liquid here, all the liquid will do is start flooding each stage. It will fill each stage. Okay. So we put in the liquid from the top, and because it is heavier, it will fall down due to gravity. We put in the gas from the bottom, and because of its lower density, it will move up the column. All right. If we have to plot, as we said before, there's the equilibrium line. The equilibrium line relates yn versus xn. And the operating line relates yn plus 1 versus xn. Okay, and once you have that, if I want to go from a composition x0 and I want to reach this stage xn. I want to reach that composition xn. Then we use a step-by-step stepping of process to work out the number of stage. We go across between the operating line and the equilibrium line. Stage 1, stage 2, stage 3, and stage 4. That will give me xn. It also tells me what the composition is, or what the composition should be coming in, yn plus 1. Okay. Similarly, if I want to go from yn plus 1 to y1, yn plus 1 to y1, I will be able to work out the number of stages, and that will tell me coming in what the composition is and going out on the liquid stream what the composition will be. Okay, so I told you on Tuesday that lots of our solutions, many of our solutions involve graphical solutions. You have to draw the graphs, etc. You must have graph paper with you. You must have a ruler, because when you're constructing these curves and these lines and these steps, etc., they must be straight lines. You can't do what I'm doing here, okay? Because if I start drawing curves or lines like this, that are not vertical and horizontal, you can see that I will get incorrect number of stages. Okay, so it must be horizontal and vertical lines. You have to do it. So you must use a ruler. Okay, bear that in mind. Any questions so far? With no questions, let's attempt this problem. Now you've got absorption of acetone in a countercurrent stage tower. Let's read the question. That's our first step in problem solving. Let's read the question. It is desired to absorb 90% of acetone in a gas containing 1 mole percent acetone. Let's understand that. So you've got a gas stream that's coming down. Sorry, that's entering the tower, going up the tower. You've got this gas stream that's coming up the tower. And initially it contains 1 mole percent of acetone, the solute 1 mole percent. 90% of that 1 mole percent you want to absorb. Okay, so you want to absorb 90% of that 1 mole percent.